Hello, everybody, and welcome to our first video in Unit 7, which is going to be all about equilibrium. So at this point, you haven't heard too much about equilibrium yet. So this is an entirely new concept that you're going to be learning in this class. All the past units, we've kind of touched on some of that stuff before, but this one is totally new. So it's kind of a nice place for us to start off with, because this is where we're going to start getting to slightly more complex topics. However, we did start to introduce the whole concept of equilibrium in class by doing that introduction activity. And you started to get a sense of what it meant in order to have established an equilibrium. And there's really two definitions that I want us to get down for this. The first definition is when the rate of the forward reaction is equal to the rate of the reverse reaction. Okay. So depending on whatever activity we did, whether it was the snowballs or whether it was the water activity, there's a point at which the rate at which going in two directions is going to be equal to one another. There's a point at which the rate at which the forward reaction is going is equal to the rate at which the reverse reaction is going. And that doesn't necessarily mean that the amount of reactants or products is the same on both sides of the reaction. You could have a lot more of one than the other, but the rate at which they are going is the same. That's one way that we know that we've established an equilibrium. Or we could say the state when the concentrations or partial pressures of reactants and products remain the same, or we'll say remain constant over time. So if you have a point at which not only is the rate of the forward and reverse reaction not being changed, but at the point at which the concentration of your reactants and products is not being changed, that's when we know when we have established an equilibrium. So we can look at this equation down here, because this is a beautiful equilibrium reaction. And here it is. So I have this cobalt hydrate complex, and this particular side of the reaction is pink. So if this reaction favors the reactants, if you have a higher concentration of reactants that's present, you would see that your system is going to be more pink. However, if I were to shift this equilibrium, so let's say I do something to this reaction and I force more products to be formed, I could have a blue solution that results from that. So if I alter this system in any way that forces the reaction to go from one direction to the other direction, I'm going to alter the rate at which that happens. But once we have reestablished what's known as that equilibrium, both directions of this reaction are going to occur at the same time. And that's what this arrow right here means. This means that this reaction occurs in both directions at the same time. So generally, we know this as an equilibrium arrow. So if I had a system at which I had this reaction in it and it was very, very pink, I would say that this equilibrium reaction favors the reactant side, right? Because I have a lot more reactants present. If I have all of these species present, but it's a blue solution, I would say I have a higher concentration of my products in that particular reaction. Let's say that I have all of these species, but the reaction is purple. That would mean that I have a relatively equal number of reactants and products. Okay, so just by looking at the color, there's a way for us to see, well, which side of this reaction is favored? Do I favor one side over the other? Do I have a relatively equal amount? But no matter where you are, even if I have a very high concentration of my reactants, the rate at which those two reactions are going is exactly the same. And that's because the concentration of each side is not being changed. So even though it doesn't look like anything is happening inside your test tube or your beaker, there is something that is occurring. So when equilibrium is reached, there are no observable changes that are occurring in the system. So it doesn't look like anything is happening, but I still have reactants forming products and those products reforming original reactants. And we say that this is what we call a dynamic equilibrium. Even though it doesn't look like anything's occurring, there's something still happening. And that's where a lot of people start to have trouble with chemistry, is they can't imagine the fact that even though there's nothing observable that's happening in a system, something is in fact happening. So if we did the snowball activity, which hopefully we did before this is being filmed, we started to take a look at something like this. So let's consider this reaction here. So I have some reaction that's occurring, and I'm just going to write the reaction here. So we'll consider the reaction, which is N2O4, and that's in equilibrium with NO2. So I could see that in this particular reaction at the starting point, right, I have a heck of a lot of N2O4, right? And N2O4 is a colorless compound. So we're going to write colorless here. I can tell that this reaction is not quite at equilibrium yet, and that's because I'm at this particular point in the dotted line. So we'll say T is equal to 0. At that point, no time has passed. And if you count the number of particles here, you have 7 N2O4 molecules, right? These are all reactants that are present. So once I start to go through with this reaction, I'm going to produce products very, very fast. Usually on this side of the line, time is going to be on your x-axis and your concentration is going to be on your y-axis. So I know that this particular blue line must be for my reactants. And that's because I'm actually starting off with some concentration of reactants, whereas my red must be the product. So I'll put products next to that and R next to there. I know that red line must be for the products because I'm starting off with a concentration of 0. But once I go ahead and I progress through this time, right, I am going to start decomposing, or this N2O4 is going to start decomposing, and it's going to start forming NO2. So after some time has passed, so I'll put some T right here, has passed, you're going to start forming some more N2O4. So if I count the number of particles here, it looks like I have 1, 2, 3, 4, 5 N2O4 particles. And I have 1, 2, 3, 4 NO2 particles. So I'm starting to form some products here, right? However, if I look at this particular graph that kind of shows this particular time, if this is at some time, whatever it is, we'll call this time of X, right? At that particular moment, we still have a change in concentration. So notice how these lines are still going up and down, right? And that's because the concentration is still changing. We have not yet reached equilibrium in this particular example. N2O2 happens to be a brown gas, which is why we're starting to see the color that's changing there. So at this particular time, we're not at equilibrium, and that's because our concentration is still changing. So I'm going to say not at equilibrium, and that's because our concentration is still changing. So let's say more time has passed. So I have some amount of time that's passing by again. And if I count the number of particles in this particular vessel, looks like I have 1, 2, 3 N2O4 particles. And I have 1, 2, 3, 4, 5, 6, 7, 8 NO2 particles. Okay. At this particular point in time, if we were to graph the concentration of N2O4 versus NO2, we would see that at some time, we'll call this a time of Y, right? Because it's different from this one. Our concentration is not being changed. This concentration at this point in time of my reactants and of my products is going to remain the same. So at any point in time beyond T equals Y, so if I'm right here, my particular reaction vessel would still contain 3 N2O4 molecules and 8 NO2 molecules. And that's because the concentration is not being changed. The number of particles is still the same. Does that mean that the reactants and products are, that the reactants are not forming products or that the products are not forming the reactants? No, those two processes are still happening. However, they're happening in such a way that they're equal. Their rates are equal to one another. So at any point in time, I will always have 3 N2O4 molecules and 8 NO2 molecules. Maybe one of these N2O4 molecules decomposes, but at the same exact time, 2 of these come together and form one more. So that's what we mean when we say their concentration is not changing. So right here, equilibrium has been achieved, and that's because the concentration is unchanged at that point in time. So there's 2 graphs that are really represented up here. So we'll take a look. There's a top graph and a bottom graph. You might see this in one of 2 different ways. And we didn't really get into the kinetics part yet. Kinetics is the rate of the reaction. We skipped that, but we could still look at a graph just to see what that means. So at this point, this particular graph on the left is concentration versus time. So I could see that when I'm at a time of 0, I have a very low concentration of products. So that's my NO2. And a very high concentration of reactants. You'll notice that the slope of the line is very steep at that point in time, and that's because your reactants are forming the products very quickly. However, that reaction rate is going to slow down until the rates of reaction are the same. So if I notice right here, this is the point at which the 2 lines are perfectly parallel to one another. So at this point, my equilibrium has been achieved. Right here, I do not have equilibrium that has been established because the concentration is still changing. I'm still forming more NO2 and I'm still using up more N2O4. On the other hand, we could also look at the rate of the reaction right here. So if I have rate versus time, again, we didn't talk too much about rate yet, but it's kind of the same thing. Once the rates of the 2 reactions become the same, that's when I have an equilibrium that has been established. And that's why I like to get both of those definitions down, because you know you've reached equilibrium when the concentration of the reactants and products is no longer changing, or when the rates of the forward and reverse reactions are no longer changing. So here the concentrations are the same. So we'll take concentration is the same. I'll just say at EQ for equilibrium. Whereas here I have rates are the same at equilibrium. 2 ways to think about equilibrium, but they both mean the same exact thing. They're both very useful when we're trying to determine when an equilibrium has been established. So let's take a look at some results from an experiment, right? So consider the following reaction and the results of two experiments. So I have carbon monoxide that's reacting with hydrogen gas, and I'm producing methane and some water vapor. Two experiments. So here's experiment 1 and here's experiment 2. If I'm starting off with 1 mole of carbon monoxide, and if I'm starting off with 3 moles of hydrogen, right? So it's starting number of moles, and I have no products, right? So this reaction has to start off going in the forward direction because I have to produce some amount of products. So this is not at equilibrium as it is because it has to produce some products. However, notice how the number of moles present at equilibrium, you can measure that, and I get this particular data, right? I get some amount of data that tells me how many moles are present at that particular point in time, given these starting materials. Let's say in experiment 2, on the other hand, I'm starting off with 2 moles of carbon monoxide, and I have 3 moles of hydrogen. So my number of hydrogen is the same, but I'm increasing my number of moles of carbon monoxide. And I get slightly different values for each of these reactants and products. It's important to note that my methane and my water happen to have the same number of moles, and that's because these are both a 1-to-1 mole ratio. So if these are 1-to-1, I'm going to produce the same number of moles. Anyway, we're going to talk about that in a different section. But even though the amount of moles of each of these particular species in this reaction is different at equilibrium, so when I increase my amount of carbon monoxide, I'm going to make more of these. There's still a relationship between this situation at equilibrium and this situation at equilibrium. And that's what we're going to get into here. So notice that the number of moles of each reactant and product present at equilibrium is different. This tells chemists that equilibrium concentration depends on the amount of starting substances. So I'm going to produce more or less product depending on how many reactants I'm starting off with. But there is a relationship between how much can I produce. And these are related by what's known as the equilibrium constant. And we can write the equilibrium constant for a particular reaction. So here is a very generic reaction right here. I'm not sure why, but they call this particular general reaction the law of mass action. Again, I don't really know why, but that's what they call that. So this is saying I have some coefficient of reactant A and some coefficient of reactant B is in equilibrium with C to some coefficient and D to some coefficient. So A, B, C, and D are your reactants or products, whereas lowercase a, b, c, and d are your coefficients from the balanced chemical equation. We can write an equilibrium constant for a particular reaction by looking at this right here. So the equilibrium constant, Kc, okay, and this C stands for concentration. We're going to talk about that more in a little bit. We got to take this equilibrium stuff step by step. The equilibrium constant is equal to the concentration of reactant C or of product C raised to its coefficient times the concentration of product D raised to its coefficient over the concentration of reactant A raised to its coefficient times the concentration of reactant B raised to its coefficient, okay? So these particular, you might not have seen this before. We have these brackets. Brackets always represent concentration. However, because we're doing equilibrium now, in our equilibrium expression, that has to be the concentration at equilibrium. So let's use this and write an equilibrium expression for this equation up here. So So it says, write the equilibrium constant expression for the reaction above and prove that the equilibrium constant is the same for experiments 1 and 2. So my equilibrium constant expression for this reaction above, let's take a look at the products here. My products are methane and water, okay? Both of these have coefficients of 1, so I don't need to put coefficients down there. So I have my concentration of methane raised to the first power, because it's only 1. I'll put a 1 there, times the concentration of water raised to the first power, over, let's look at the reactants. Looks like I have carbon monoxide raised to the first power and hydrogen raised to the third power. So I'm going to put carbon monoxide raised to the first power. And hydrogen has a coefficient of 3, so I'm going to raise that to the third power. That is my equilibrium expression for that particular reaction that was represented above. So we want to show, is the equilibrium constant, is Kc going to be the same value for experiment 1 and for experiment 2? So let's go ahead and look right here. Let's do experiment 1 first. Let's plug in our values for methane. So I'm going to use these values at equilibrium, okay? We're going to assume that this container is 1 liter. So we'll see the volume of this container is 1 liter. So therefore, rather than moles at equilibrium, if it's a 1 liter container, this would be the concentration, right? That's something that we'll get into later in the unit that really should be specified up here, but it's fine. So all of these will be in concentration because we'll assume it's a 1 liter container. There we go. I'm just going to plug these into my equations down below. So for experiment 1, concentration of methane is 0.387 raised to the first power times 0.387 again raised to the first power. That's for water. And I'm going to set that over concentration of carbon monoxide is 0.613 times my concentration of water vapor, which is 1.84 raised to the third power. And if you solve this correctly, you should get an equilibrium constant of 3.93 times 10 to the negative 2. This is actually a unitless value. So you don't even need a unit for this. There is no unit that's present for that. Let's see, do we get the same equilibrium constant for the second experiment? So that's what we're going to see. So experiment 2, let's do the same exact thing. I'm just going to plug in these concentrations at equilibrium instead. So Kc is equal to 0.478 times 0.478 over 1.52 is my concentration of carbon monoxide. And my concentration of water vapor is 1.57. And I'm going to raise that to the third power. And if you solve for this correctly, you find that your equilibrium constant is basically the same, right? We're off only to the hundredths place. These numbers are practically the same exact value. So we can see that even though I'm starting off with a different amount of products, at equilibrium, I still get the same ratio of reactants to products. So their equilibrium constant is exactly the same, okay? And that's what we're going to find at equilibrium for each one of these. Here, let's go ahead and just write the equilibrium constant expression for each of these reactions. We're going to do the same exact thing. Notice that A is just the inverse of the one we just did. So it's always going to be the products over the reactants. So my concentration of carbon monoxide times the concentration of hydrogen cubed over my concentration of methane times my concentration of water vapor. So that is my equilibrium constant expression for this particular reaction. It's basically just the inverse of the last one because, of course, my reactants and products are flipped. Let's try it for this one here. So my equilibrium constant expression, a lot of times it's just represented as K. So I'm just going to write K here just for reasons we'll talk about later because there's a lot of different types of K, but no worries. It's for a different section. Same exact thing. Concentration of my reactants raised to the first power because its coefficient is 1 over my nitrogen raised to the 1/2 power, actually, times hydrogen raised to the 3/2 power. Yes, you can have fractions. Is College Board going to give you fractions? Probably not, but it's always good to see some because it's the exact same thing. This one we actually did before on that first page. So if I was to write my equilibrium constant expression for that nitrogen example, concentration of NO2 squared over my concentration of N2O4 to the first power, okay? I got a lot of coefficients for D, but that doesn't necessarily make it any more difficult. So I'm going to take my concentration of my products, NO2, I'm going to raise that to the 4th power. That's going to be multiplied by water raised to the 6th power over concentration of ammonia raised to the 4th power times oxygen raised to the 7th. Same exact thing. Reactants or products over reactants raised to the power of their coefficient. Very simple to represent an equilibrium expression. So let's use this information and do sample problem 3. So we're going to write equilibrium constant expressions for each of these individual reactions. And then we're going to calculate the value for the equilibrium constant. So let's first write the equilibrium constant expression for this reaction. So the value of Kc is equal to, I have ammonia raised to the 2nd power over my nitrogen to the 1st power and my hydrogen raised to the 3rd power. All I'm going to do, and I'm given the equilibrium concentrations, so I'm just going to plug these values into here, and I'm going to get some number. Just to save a little bit of time, I'm going to save you from writing that out. You should do that, though, and you should get a value of 3.8 times 10 to the 4th, okay? Let's think about this. So what does this mean? What side of the reaction is favored? Who is there more of present at that time? Are there more reactants that are there, or are there more products? If I get a value that is much greater than 1, so I have a number that's like 38,000 at this point, right? This must mean that my concentration of ammonia is very high. Because if I have a very high concentration of ammonia and a very low concentration of products or of reactants, I'm going to have a very large value. So because my value for K is so large in this case, I know that this particular reaction must favor the products. I have a heck of a lot more NH3 that's present there, and that's because my value for K is so large. So not only can I calculate the K, but that value of K tells me quite a bit about whether or not a particular reaction at equilibrium is reactant favored or if it's product favored. In this case, because my value for K is so high, that must mean I have a very large concentration of ammonia relative to the reactants, which gives me a very high value. So let's try this one here. Notice the reaction is flipped, right? So in this case, my N2 and my H2 are in my products and my NH3 is my reactants. So Kc is equal to, always going to write products over reactants raised to the power of their exponents, NH3, 2. And all I'm going to do here, again, is just input these numbers, right? So you try that. And if you do it correctly, you should get a value of 2.6 times 10 to the negative fifth. Notice that this value is very small, right? So when I flip this reaction, I have a very small value for K. This must mean that my amount of my products in this case is very small relative to my concentration of my reactants. If this value is very small for my products, but if my concentration of my reactants is very large, I'm going to get a very small value for K. So in this particular example, this reaction favors the reactants because K is much less than 1. And that makes sense because if I flip this reaction, right, in this case, NH3 was on the product side, and I said that the products were favored. Here, if that NH3 is on the reactant side, my value for the equilibrium constant is going to represent that it favors the reactants. Okay, so you're going to see lots of connections with this as we progress through this. And again, it all comes down to the math. So if you can think about these fractions and okay, if I have a large amount of NH3, if I have a high concentration of that, but a very low concentration of that, it's going to give me a large value of K, which means that I favor the products, and the opposite for the, or vice versa. You could which side of the reaction is favored. And let's try this last one here. So notice how I am using that original equation from A, but I am raising it to different powers. So K is equal to concentration of ammonia to the first power over my concentration of nitrogen to the 1/2 times my concentration of hydrogen to the 3/2. And if you solve for that correctly, again, using those numbers that are up in here, okay, those concentrations, you should get an equilibrium constant of 1.9 times 10 to the second. So still have a very large value. I have a high value for K. It's greater than 1. So because this value is greater than 1, again, we could say that this particular reaction is going to favor the products. My concentration of products is very high relative to my concentration of the reactants. And that's because if this number is very high and if this number is very low, that means that my value for K is going to be large. You heard me say before there's a couple of different types of K or some variations of K, right? Ultimately, they all mean the same exact thing. We're just getting a little bit more concise when we talk about this. So you've already seen just Kc. C is going to represent the concentration of reactants and products. So you're going to see Kc used a lot, especially with aqueous solutions. All right, aqueous solutions. And of course, that's because I could change the concentration of aqueous solutions. I could have a 0.1 molar hydrochloric acid solution, or I could have a 3 molar, or I could have a 6 molar, right? Concentration of that is changing. And when I tend to use concentration values, we represent C in that case, so Kc. Sometimes you might see Kp, and Kp, it's the same exact expression, right? You're going to represent it the same exact way, except you're going to use the P in this case. So notice how I'm not using the brackets to represent concentration. I'm using a capital letter P to represent the partial pressure of gases. And this is only true for gaseous reactants and products. And I could change the concentration of gaseous reactants and products because, of course, if I have a change in pressure, the higher the pressure means the more concentrated a particular gas will be. So it's the same exact expression, just rather than brackets, I'm using the partial pressures in place of that. Sometimes you might see KEQ, right? And KEQ is just a very general equilibrium constant, right? It's used for anything. So you might see KEQ in place of KP. You might see just K in place of either of those, right? But ultimately, they all mean the same exact thing. And you would write the equilibrium write the equilibrium expression the same exact way for each of them, just a little bit representations of each of those depending on the type of reaction. So here's a nice example in which we're working with gases with partial pressures. So sample problem 4 says the reaction for the formation of nitrosyl chloride is represented there. The pressures at equilibrium were found to be, there's our equilibrium pressures. We want to calculate the value for Kp. So it's the same exact expression. Kp is equal to, but in this case, rather than concentration, I'm going to use the partial pressure of NaCl, and I'm going to raise it to the second power. So it's partial pressure in this case, over the partial pressure of NO raised to the second power times the partial pressure of Cl2 raised to the first power, okay? So even though I'm not using the brackets, I'm still going to plug these numbers in the same exact way, but we're being a little bit more concise here because these are not concentrations. These are technically partial pressures. So again, I'm going to save you the time here, but if you plug all of these values in for here, you should get a final value of 1.9 times 10 to the third as our equilibrium constant. If I were to ask you what side of the reaction is favored, would this particular reaction favor reactants, or would this particular reaction favor the products? Because this equilibrium constant is very high, that must mean that I have a high partial pressure of my products. So in this case, this particular reaction favors the products. At equilibrium, I would have more products that are present, okay? Equilibrium doesn't mean that I have an equal amount of reactants and products. It just means the rate at which the reactants are forming products and the products are forming reactants is the same, okay? They're not necessarily equal. We're going to wrap this up here. Hopefully this last page is not going to take us very long. When we talk about partial pressures and when we talk about concentration, right, I can change the concentration of each of those, okay? So if I have, for example, a solid material, or if I have a liquid, if I have solid iodine, let's say, and if I add more iodine to a solution, I'm not changing the concentration of that iodine. I'm just adding more, right? So when we are writing equilibrium constant expressions, we do not have to add in solids or liquids. We are only going to represent aqueous solutions and gases. And that's because only in these two scenarios do concentrations change, okay? Equilibrium only comes down to a change in concentration. I cannot change the concentration of a solid. If I add more solid, there's just more solid there, right? If I add more of a liquid, I'm not changing the concentration of the liquid. I'm just adding more. For example, if I have water in its liquid state of matter, if I add more water to a flask, I'm not increasing the concentration of water. I'm just adding more water, okay? And we have to keep that in mind when we write equilibrium expressions. So let's do sample problem 5 together very quickly. Write the equilibrium expression for the following heterogeneous reactions. Heterogeneous just means we're working in more than one phase. So, the decomposition of solid phosphorus pentachloride, and this is a solid, to form liquid phosphorus trichloride and chlorine gas. Chlorine gas is a diatomic. It's one of our Bofinch atoms. So if we were asked to write the equilibrium expression for this particular decomposition reaction, you have to consider that there are solids here and there are liquids here. And we cannot change the concentration of a liquid because, again, all I'm doing is just adding more. So my equilibrium constant expression would be, because this is a gas, we're going to use Kp. Kp is equal to the partial pressure of Cl2. That's it. Because I only have one species in this reaction that could change concentration. And that species is the gaseous diatomic chlorine, which is in the numerator because it's a product. Let's try this second one here. This is asking deep blue solid copper 2 sulfate pentahydrate. So pentahydrate means there are 5 water molecules. Is heated to drive off water vapor. So I have some water vapor coming off. This is a gas. This is a solid. And I have white solid copper 2 sulfate. So I'm basically just heating this up to get rid of all of those water molecules. Again, I cannot change the concentration of solids, so they are not represented in my equilibrium constant expression. This we avoid, and this we avoid. Because if I add more copper 2 sulfate, it's not changing anything, right? So I would represent my equilibrium constant expression. I'm going to use Kp here just because this is a gas. That's equal to the partial pressure of water vapor raised to the 5th power. It's important to keep those states of matter in mind because, yes, water is a liquid at room temperature, but because this is a gas, I could change the concentration of gas because if there's a higher pressure of gas, there's more mass per unit area, right? Which then ultimately increases its concentration. So because we're talking about water vapor in this case, we do have to be aware of that. Let's just go ahead and get this down. We already started to talk about this. If I have a very large K, that means that we would favor the products, right? For reasons we've already talked about. If that numerator is very high and if that denominator is very low, that's going to give me a very large value of K because my concentration of products is very high. If I have a very small value of K, we're going to favor the reactants for the opposite reason. And if I have a K that's a 1, close to 1, that means that I have a relatively equal amount of both reactants and products. Their concentrations are about the same. I have a relatively equal amount of each of those that are there. Pretty long introduction video, but this kind of just gets the gist of a lot of things. And actually, this crosses off quite a bit of stuff off of our CED, so off of everything that you need to know. We talked about quite a few things already that we can cross off on our board in the front with the little Post-it notes. I know this is very different. I understand. So as always, if you have any questions, please reach out to me. We're going to work with this for quite a while. I promise. Do not get overwhelmed. And as always, I will see you in the next video where we start talking about equilibrium constants versus the reaction quotient. So I will see you then. Bye.